Hello, welcome back to CE366 Geotechnical Engineering 1, Lecture 2, Index Tests and Soil Classifications. In this lecture, we will achieve two objectives. The first objective is for you to understand the Geotechnical Index Tests, including Sieve Test, Hydrometer Tests, and Algebraic Test. The second objective for this lecture is at the end, students should be able to perform soil classifications per USCS, which is the Unified Soil Classification Systems. So soil classifications. So what is soil classification systems? What we try to achieve here is to classify soils into different groups of material with similar engineering properties. So to get this job done, we think of what kind of different factors is affecting the engineering properties. So if you're given like soil samples, you think of like what type of factors are affecting these properties. And there's different factors we can start with. First, each soils is make up of each different soil types is made up of different of mineralogy. And this topics, the mineralogy of soils, is into the topic of clay science. And this is an engineering course. We don't have too much time to cover this topic. And we typically will talk about this in better details in the graduate level class, CE566, and you will like take us like a couple of lectures just to talk about the background of different type of soil origins, and also the chemistry of soil particles, soil minerals. And but if you're interested in this topic, I highly recommend you to read chapter 2.2 to 2.5 of the textbook. It will give you enough backgrounds to cover just enough knowledge in these topics. So the second factors that affect engineering properties is the particles characteristics. Which means the size, the shape, and the texture. So knowing the size of like different particles, imagine that they're very straightforward. If you know different size of particles, it will help you to know how to classify them, so you can draw the boundary. Whatever larger than this or whatever smaller than this size, then it belongs to different groups. And also you can do it for the shape and the texture too. And the third factors that affect soil behavior is just the structure of the soils. So imagine that for sand type of materials, the structure of sand is the density. And for the clay type of material, what affects the structure of the soils is the fabric. And the fabric of the clay can be like going to two kinds, just like the density of the sand. You can have a loose density, or you can have a dense density. For clay is a little bit more about the mineral of the materials. So it's a little bit complicated when you try to describe the different structure of clay. But there's two different type of fabrics of clay. This is the dispersed one, or the folliculated one. So the dispersed like clay fabrics, you could think of like a bunch of a card, they stacking on top of each other, because the clay particles, the shape of the down to element level of it is kind of like a sheet type of particles. So it becomes a little bit cards. How to organize them? You make up the fabric of the clay. The other extreme is just like you're playing with the card. You can form a house. So if you like getting the edge of the card like on top of each other, and then you can form a kind of like a loose configurations, and that is the folliculated fabric of clay. So the different structure of the soils can also give you different type of engineering properties. The last type of a characteristic of soil can have is the time dependency. Which means the aging aspect of soil. If a soil sitting, situated on the ground on the site for 1,000 years versus 10,000 years, the time pass by, and you will have a different soil properties. So the agings of the soils matters too. So what? Don't forget, like, so we just list out a bunch of different like factors affecting engine properties, and our key missions here, our main goal here, what we try to achieve, is we want to find out one particular characteristic that can help us to do our job, which is soil classifications. And we are engineers. We like things that like simple enough that we can get done quickly. We can get to our solutions quickly. So we are engineers. We are rather than scientists. Scientists will spend unlimited amount of time to try to solve for one problems. But we're engineers, like we need to move on from project to project, and we will only spend like a fair amount of time to make enough assumptions for us to move on to get our job done. And one very importance or very like a simple like a characteristic we can take advantage of is the size. It's the size of the particles to help us to do soil classifications. Again, the size of the soil particles to help us to do soil classifications. So the picture on the right hand side here, we have three different main type of soil right there: the sand, silt, and clay. And sand, if you look at the particle of the sand, you will have the largest size among the three different types. It's about 0.05 millimeters to 2 millimeters of particles. And then if you have that size, we classify that as a sand particles. And for the clay, it's very small. If your clay particles in general is about less than 0.002 millimeters. So this is a typical like a clay size, and you even cannot see it with your eyeball, and it just kind of like a card shape or sheet shape type of particles stacking on top of each other to form the clay samples, the clay soils. And in between the sand and clay, we have the silt. We have the silt type, and the size of silt is in between the sand and clay. In order to do our geotechnical soil classifications, we need to understand the geotechnical lab testing, because that is the approach for us to do soil classifications. So this class, this lecture introduces you three different lab testing. For soil classifications. And the first type of lab testing is the Sieve Test. And the second type of testing is the Hydrometer Test. And combining these two tests will give you the grain size distributions. So we'll come back to each test individually to talk into more details. And actually, if you take the next class, C368, you will have the hands-on experience on doing like this test. And pretty much like the Sieve test and Hydrometer test there is helps you to tell the particle size. So that's why the two tests can help you to form the grain size distribution curve. And the third test we will cover in this test, and also very typical for geotechnical testing, is the Algebraic Test. And this test is mainly for the fine grain material. Which is the clay and silt. So we talk more about what is fine grain material. But this slide just want to give you an overview on what type of testing they are available for us to do the jobs of soil classifications. So first, Sieve Test. So what is a Sieve Test? So again, we want to measure the size of the particles, and the most obvious ways to do it is using a bunch of different sieve with a different opening size. So a sieve test is pretty much just a stack of sieve with different size of openings in the bottoms, and you stack up the sieve, and then you will put your soils at the top of the top sieve, and then you go through the shaking. So with the shakings, the different type of soils with different size of particles will kind of pass through the sieve. If the size of the particles is small enough to pass through the sieve, so such that at the end of the day we can calculate the percentage by weighting of each sieve, how much soils retained on there. And with that, we can know, for examples, maybe all of them passing the highest sieve, then we know that all of the soils particles is smaller than the opening of that sieve. And for a standardized sieve test, we have different size of sieve, from sieve number 4 to number 200. So the size of number 4 sieve is 4.75 millimeters. So as you can see on the picture, this is a number 4 sieve. So the opening of the mesh over there is 4.75 millimeters for each of the square openings. And when we all put the sieve, again, you will be the largest opening on the top and the smallest in the bottoms. And in a sieve test per ASTM standard. So ASTM stands for American Standard for Testing Method. So it's a professional's kind of a reference that everyone can reference to. So per ASTM standard, the smallest size at the bottom of a sieve test is 0.075 millimeters. And as a geotechnical engineers, those sieve numbers and size, particular for number 4 and number 200, is the one that we assume everyone can memorize and understand, or is part of the terminology or the language, geotechnical language that we need to pick up as a geotechnical engineers, because those two sieve defined the material that the different type of soils that we will deal with. So 4.75 millimeters, number 4 sieve, is the difference between gravel and sand, which means whatever retained on number 4 sieve, that defined as gravel. So if your soil particles after the shaking is retained on number 4, which means the soil particles has a size greater than 4.75 millimeters. So if the soil passing through number 4, which means the soil particles, they become sand. So whatever passing number 4 is only just sand. It could also be silt and clay. So that make another sieve, number 200, become important. So number 200 sieve means the size of 0.075 millimeters. So whatever passing number like a 200, that means the soil particles is smaller than 0.075. That means that's a silt and clay. And between the number 4 and number 200, that would be contribute as the sand particles. So that's why, like, picking up this terminologies is important, because when you talk with a professional geotech engineers, they expect you to know. For example, they will tell you, you have material passing number 200. For example, your site has like a lot of material passing number 200. Then you should concerned about the settlement issue, which means like when people tell you, you have something passing number 200, then you know that this is silt and clay. And for silt and clay, we have another term for that. We call fine-grained material. And for the material that is above number 200, retained on number 200, we call them to be the coarse-grained material. So those are the terminology that we need to pick up here. And also in a way that you need to be really good on this kind of speaking this language like fluently, because people can tell you you have material retained on number 4, then people expect you to know that they are talking about gravel. And you have something passing number 4, it would not be just sand. If something passing number 4, it could be sand or silt or clay. So those are the terminology that we need to pick up. So after we have the Sieve Test, then we are able to generate the grain size distribution curve, at least part of it. Because because the size of the sieve, so which means the size of the particles. And in order to represent our results as a grain size distribution curve, we plot out the results in a semi-log scale. So per ASTM standard, this got to be in a log scales. So the x-axis is the particle size, and the particle size is determined by the sieve openings. So that's why, for examples, when we have a number 4 sieve, it is 4.75 millimeters. So if we go to 4.75 millimeters on the semi-log scale on the x-axis, so you need to know how to read a log scale. So this is 1, this is 2, 3, 4. So this is 2, this is 3, this is 4. And 4.75 is right there. And this means like a sieve number 4. So you know that sieve number 4, whatever retained on it. So this is the retained on number 4, which means this is gravel. And whatever passing number 4, this is sand. So whatever passing it, number 4, that would be sand. Actually, not just sand, right? You could sand, silt, or clay. And very similarly, another very important sieve size is number 200. It's a 0.075 millimeters. So this is 0.075 millimeters, and that represents the number 200. So on the x-axis, you can identify the particle size based on the Sieve Test results. And if you walk through assignment 2, so if you work through your homework number 2, you got you give your Sieve Test results, and you're required to calculate or to change the data on a grain size distribution curve. So by percentage of weight passing each sieve, then you should able to calculate the percent passing. So that will be the y-axis, and then that will give you the grain size distribution curve. So for examples, on this chart, we have 3 test results over there. We have 3 grain size curve. So we have the square, for examples, representing the sample number 1. The triangles represent samples number 2. And the circle is a bit hard to see, but there's another sample number 3 right there. So if I read this graph, then for examples, for my square right there, sample number one, if I want to know the percent passing number 200, then I will find like my square curve is pretty much, is a bit hard to see, but this is my square curve right there. This is about 94% passing number 200, because if you go back to the y-axis, that is 94%, which means like most of the soil particles from these samples is small enough that passing through number 200 from the Sieve Test, which means this is the majorities of this soil samples is fine grained materials. This is clay samples or silt samples. Okay, for hydrometer test. So this test is we will cover into more details in the laboratory course CE 368 again, because in the lab, then we will be able to spend more time with the equipments like in front of us. Actually, have hydrometers setups that you can hands-on work on. So we don't spend too much time here now, but instead, we can spend about 30 to 45 minutes just talk about this in the lab during the lab class. But anyways, for this test, my expectations for you to at least to understand that is we need this test to find out the diameters of the particles, because for soil classifications, the main particles characteristic we take advantage of now is the size, right? The size of the particles. But it can become a problem if the soil particles becomes too small. So remember, number 200 Sif, it is at a size of 0.075 millimeters already. So if we take out that Sif, pretty much you become a mesh that you even have a hard time to see the openings with your eyeballs. Go smaller than that, then it becomes too expensive to create and to maintain such mesh openings. So that's why for passing or for a particle smaller than number 200 Sif, we have a better hope that we take advantage of the sedimentations analysis, which means what happened analysis, we try to find out the particle size indirectly through the mixture of our soils with fluid. So the soil water mixture, when you try to shallow or you a sediment during this sedimentation process, you will create uh, a fall down velocity. And according to the Stokes law, the when you an object when you fall down, the when you reach the terminal velocity, the diameters of the particles is proportional to the square root of the velocity. So that's the Stokes law, and we take advantage of this Stokes law and the sedimentations analysis, such that to help us to indirectly measure the diameters of the particles. So that's the concept of hydrometers. The details of it, we will discuss it more in CE 368, hopefully inside laboratory. But again, what happened here now is what we try to achieve is to find the diameters of the particles, take advantage of the Stokes law, because the terminal velocity of a falling objects, the velocity of the falling objects, the square root of it is proportional to the diameters. We cannot measure the diameters, but we can measure the velocity, because the velocity is equals to the distance traveled divided by time. So the length divided by time right there. So if we can measure those two terms, then we can calculate the diameters. So that's the concept of hydrometers. That's why I asked for this class, is understand this concept and also why we need to do it. It's because the particles is too small to be physically use a sieve to determine the particle size. And the particle size is the key. So now with the hydrometers, this is the same three test results. That's three seems like a grain size distributions curve that we looked at like about 2 slides ago. But now, like in addition to the Sif test results, we also have the hydrometer test results. So combining the Sif and hydrometer test results give us the complete grain size distribution curve. So if you have a sand soil samples, then pretty much everything stop at number 200 because all of them is retained on number 200. So your grain size distribution curve pretty much just stop at number 200. You don't need the hydrometer test. But if you turn those your soil samples we took from the field, you have both uh, the clay and silt and also sand particles. Then like urea 1-2 test, Sieve test, and whatever go through the number 200 passing number 200. You will collect it, and then when a hydrometer test, then you can complete your grain size distribution curve to see at different size or particle size how much percent passings of that particular particle size. So once we get our grain size distribution curve, there's a little bit more to discuss in greater details. Is you need to think of how the size distributions to come up with the shape of the curve. Because, for example, we are seeing three very different shape of curve here. So this the grain size distribution curve. Again, the x-axis are the particle size, and the y-axis is the percent passing. So percent finer means like a percent passing. And if we have three curve, and in fact, if you look at it, you could have like three different very uh, different types of shapes right there. You could have a shape like the yellow one that like kind of like uniformly like a very gentle slope, or like you can have the green one that uh, you pretty much like you have a strict line, a vertical strict line portions right there at some point of the curve, or like you have like a kind of like a two parts right there. So there's a one part of like a curve, and then suddenly you have that another curve, and another part of the curve, kind of like I have a gap between like a two portions of the data. So those different shape of a grain size distribution curve, in fact, giving us some hints on how the grain size distributions look like. So if you have like again here like a curve 1, 2, 3 over there, you can think of like if the soils itself, how does this look like? Because at the end of the day, remember how we come up with this grain size distribution curve. Yes, originally we have a soil samples that we collect from the field, and then we put the soil samples on top of on top of a stack of sieve, and then we do a Sieve test, and whatever passing number 200, we do a hydrometer test. So after we have all those like a data, then we can plot out our grain size distribution curve. So now we're kind of working backward. Now we have the curve, and then think of how would the grain size distributions or like actually in fact how is this distributions of soils look like? Because like if you're engineers end up like what you get on your desk or on your report is not a soil samples but like a soil report. So if you're civil engineers, any phase of any civil engineers, like you will any civil engineering project, there got to be a geotechnical report, or people call down to the soil report to represent like on the project sites, on the foundation for your foundations, what type of soils you need to deal with. and you don't have a soil samples many times because those have already been done like by geotechnical engineers and become a soil report or geotech report that like be used to communicate with the structural engineers, with the architect, and whatever, so on and so on, or even the clients. And at the end of the day, what they need to as a geotech, you need to explain to your colleagues on this curve, what does it mean? What kind of soils you have? So if you think about this, you have three different type of shapes right there. For example, so if we look at like a shape number one, like the green curve here, what type of like a soil particles you could have? What being special or what making like a curve number one difference than the other two is you kind of have a strict line portions right there, which means, right, the strict line portions mean what? Means like there's like a large percentage of soil particles is at that size. Because remember, think about this. Because if you have this like a strict line portions right there, so this is the strict line portions, which means that you have like a quite a bit of like a soil percent passing belongs to this particular size. So for example, like this graph here telling you like almost like 50%. So this is about 70, this is about 20 right there, about the difference 50. So about 50% of soils is at this particular size. So if you want to visualize this, right, you have four options right here. One, two, three, four. So which type of like a soil particle combinations over there, giving you a kind of like the grain size distribution curve like the green one here. So very likely would be like perhaps maybe like this one. And we call this if there's like a one size dominant of soil samples right there, we call this to be poorly graded. So again, just like some terminology that we need to pick up for this class. Uh, so this is a poorly graded soil, poorly graded soil distributions. So the other one, well, maybe so this is poorly graded. Maybe this one is also poorly graded. So the next one, curve number two, you can think of. Now you have a curve that like pretty much you have a gentle slope, kind of like a constant slope throughout like spanning through all the particle size. So which means this is uniformly graded, which means like the soil particle size are uniformly distributed, which means like you have a good representations of everything. You have good representations of any different size. Some people call it uniform graded. Some people call this like a well graded. So well graded or uniform graded. So if you look at this four picture right there, perhaps this one's is well graded. It looks like it is, but it's arguable in fact. Without like engineering systems, if you just do this by eyeball, you may have a hard time to determine well grade or like a poorly grade. But like the concept here is being well grade means like your soil samples has a good representations, equally like distributed by percentage of like every size over there. Last but not least, um, our final curve number three here. If we have like kind of like a two domains, so what being special on curve number three is kind of like you have two domains right there, and we call this to be gap graded. So visualizations of samples, maybe this one. Is a gap graded like a soil. So you have like kind of like two dominant sides work there. There's a gap between the two sides. So if you do all this just by eyeball, you'll be on the soil samples physically, you'll be really hard to tell. Is that truly well graded or is this truly poorly graded? Some extreme case like like this one here is obvious like it's poorly graded. But like very likely natural soils is a bunch of everything. So it's very hard to just tell by eyeball such that we need engine systems. We need an engine systems to help us to quantify, using numbers to quantify, to define what's being well grade and what's being gap grade. And according to ASTM standard D2487. So by the way, ASTM D2487 is available on CanFacts. So if you want to learn more about this or read the a technical reference, feel free to go to the STM standards. So when you go to work or when you're practicing engineers, you cannot reference the textbook because no one's know about which textbook you're talking about because your textbook may be very different than the textbook that 20 or 30 years ago. But what BNQ are always are professionally engaged and also update the ASTM standard. So I highly encourage you guys, at this stage of our career, try to get used to reading those ASTM standards. Yes, there's a lot of jargons, there's a lot of technical language over there. It may take some time to get used to it, but the sooner you get used to reading those like a professional reference, the more it will help at the beginning of your career. So I recommend you try to read the ASTM standard. But anyways, the ASTM standard 2487s, you recommend like a procedure right here, using a bunch of different parameters to help you to define what being well graded and what being poorly graded. At the end of the day, being well graded and poorly graded is required for soil classifications. So the purpose we are doing all this here is helping us to do the soil classifications. So they create two parameters for C sub U, coefficients of uniformity, and C sub C, coefficients of curvature. And those parameters is defined by D60 and D10, and also D30. So a D30 means the diameter is at 30% passing. So when you have a grain size distribution curve, you know at 30% passing, what is the corresponding diameters. Same as 610 and 60. We will do examples after this so hope you help you to visualize what is D10, D60, and what is D30. So after you calculate the C sub C and C sub U, the STM standards define that in order to be well graded, your C sub U is greater to 6. And also C sub C need to be between 1 and 3. So if you fulfill those two criteria, which means your soil samples on the grain size distribution curve is well graded. Pretty much if you can imagine this as if you fulfill these two conditions right there, you kind of have a constant slope. You will kind of have a constant slope grain size distribution curve. And if you don't fulfill these two criteria, very likely you will have kind of one size dominant it's kind of like a curve right there. And in that case, the two criteria again, it becomes the C sub U less than 6, and this is all conditions that C sub C greater than 3 or C sub C less than 1. If that is the case, then your grain size distributions is poorly graded. So furthermore explanations of this. So again, what is D60, D10, and D30? For example, this is strictly from the ASTM standard, like a figure 5. So they do have examples within the ASTM standard. So for example, like this curve. So this is the grain size distribution curve. So you have your particle size as the x-axis and the y-axis to be the percent passing. So this is what we have been like seeing for our grain size distribution curve. So this is your grain size distribution curve. So D30 means like a 30% passing. So this is 30% passing. What is the corresponding particle size diameters? So when you need to determine D30, what you will do is like go to your grain size distribution curve on the y-axis, go to 30%, and then like find the corresponding x-axis reading. This case is 2.5 millimeters. So your D30, the diameters at 30% passing for this examples is 2.5 millimeters. Very likely 60%, the same concept. So y-axis at 60%, you go to the curve and find the corresponding x readings. This one is 15 millimeters. It's 15 millimeters. So those are the two D10 and D30 and D60. Then also D10, 10% passing. Whatever you read from the grain size distribution curve, that would be your D10. That would be D10. And the coefficients of uniformities is defined by D60 divided by D10. So for example, this one, we know D60 is 15 millimeters, and D10 would be 0.075 millimeters. So with that, you can calculate the C sub U is 200. So the same thing here for the coefficients of curvature. So you need to identify D30 first. For this case, is 2.5 millimeters square. And then D60 is 15 millimeters. And D10 is 0.075 millimeters. And if you do your math, everything cancel out, it's 5.5. It's 5.5. So after you have the C sub C as C sub U and C sub C, you need to determine whether this is well graded or poorly graded. And the criteria for being well graded is you need to be greater than 6. So the C sub U, so if you draw the inequality line, so we have 6 right there. You need to be greater or equal to 6. And this is N scenario between 1 to 3. So this is the C sub U, and this is the C sub C. Need to be between 1 and 3. So for our examples, like we just done, so we calculate our C sub U is 200. So you fulfill the first case, and like C sub C is 5.5, which is not between 1 and 3. So it didn't fulfill the requirement of C sub C. So which is the case that this is not well graded. This is poorly graded. Because in order to be well graded, you need to fulfill those two conditions. So this case is poorly graded. So to finish this slide, again, like let's look at the case for the poorly graded. If we draw our inequality, first of all, it need to be C sub U to be less than 6. And this time, this is an OR case, not an AND case. So if you fulfill like it doesn't need to be like fulfill all the conditions in order for it to be fully graded. So it will be the case that in 1 and 3. So this means like a C sub C greater than 3. C sub C, and the other part here means C sub C is less than 1. So this is our OR case. So C sub C either like greater than 3 or C sub C less than 1, or the case will be give you the poorly graded. And our examples again, we have C sub U equals to 200. It didn't is it is like greater than 6. It didn't fulfill this case, but like the C sub C is like equals to 5.5. You fulfill this case, and since this is all conditions, so it works for the poorly graded soil. It works for as a poorly graded soils. So one more examples. We do it here together. So here we have C sub U equal to 7 and C sub C equal to 5 is a poorly graded, well graded, poorly graded. So if C sub U is equal to 7, so if we're checking for well graded, yes, it is fulfill like the first case. But C sub C is equal to 5, which is not between 1 and 3, so it is not well graded. But when we check for poorly graded, first of all, C sub U is greater than 6, so it's not fulfilling the first criteria. But like a C sub C of equal to 5, which is like greater than 3, so it fulfills this case. And since this is all conditions, so it works as a poorly graded soil. Okay, moving on. The third type of testing we will cover today is the Algebraic limits. Unlike the previous like a testing we talk about, which is the grain size distributions that have two tests, the Sieve Test and Hydrometer Tests. Those two tests are for finding out the particle size. But this one, Algebraic Test, is a little bit different. This one, Algebraic Test, focus on fine grains materials only, which means only a silt and clay, and mainly is try to figure out the amount of water is focused on the effect of water on those fine grained soils. It has two main purposes for this test. The first purpose is to tell the state of the clay or the silt. So when we say state, there's a three state that being possible for clay and silt. You could be at a solid state, you could be a plastic state, or you could be a liquid state. So that's the first purpose, to tell us like this test to help us to identify what kind of state it is. Is the soils that you have on site? Is that like being as a solid, plastic, or liquid? The second purpose for this is to help us to do soil classifications. So what are the Algebraic limits? All are the Algebraic limits. Algebraic limits actually like it has like two main components. There are three limits, but like for our engineering applications, we focus on two, which is the liquid limit and also the particle limit. Liquid limit and particle limit. So Algebraic limits, we mainly look at two: particle limit, liquid limit and particle limit. So Algebraic limits again, like you need to understand what is liquid limit and particle limit. So what is liquid limit? Liquid limit is the water content. Is the water content of the soils. So every different soils we will have different like a liquid limit, but the liquid limit is the water content that defined the soils is between the state of plastic and liquid. And particle limits means the threshold or the white amount or like a specific water content that defined the two states, the solid states and the plastic state. And if you understand like this chart over here or this diagram here, then you will understand what is Algebraic limits. Because soil or clay, if you think of like clay still some samples, uh, the behavior of it, the state of it, highly depends on the water content of it. So imagine like if you have a clay samples or clay soils that like you can play with. If you make it like a oven, if you like put it in the oven, and then like you make it completely dry, which means there's no water at all within the soils, then the whole thing behave like a solid. So you have the water content equals 0. So this the x-axis on this graph is the water content. If you get rid of all the water, you behave like a solid. It could be like a powder, or it could be completely dry. And if you keep adding water on it, and if you mix it with water, the more water they add on it at the beginning, you'll be still like become like a solid, because the water is still trying to fill up the void of your clay. And at some points, the volume will start to pick up, because now like your void is saturated with water, and any extra amount of the water to add in, you increase the volume of the water and clay mixture. And at some point, like now, if you add enough water, then like at the right amount of water content, you will be right at the boundary between solid and plastic. So that will be the plastic limit. So like now like when you starting to become like a plastic, your dry clay, which behave like a solid, maybe now is like start to behave like a butter type of like state, or butter type of material. And then if you keep adding water on it, and eventually you will like transform like the clay state or the soil state from plastic to become like a liquid. So that between the state of plastic and liquid, we define the water content at that particular level is the liquid limit. So there's also strain gauge limits, but like for our soil classification purpose, all we need is the plastic limit, and the liquid limit. And also there's come with another terminology, what we call the plasticity index, is defined as the difference between the liquid limit minus the plastic limit. So the difference between the two will be the plasticity index. So you imagine that like if you have a higher plastic limits index, if a large values of pi, which means like the soil can hold a lot more water, because now the plastic state on this diagram is much wider. Also, there's another terminology called liquid index, and the formula is the water content minus the plasticity index divided by um, the liquid limit minus the plastic limits. Again, like the liquid index will kind of give you an idea how liquid of the soils that you can have. So this is the water content. So those like a plastic limit and liquid limit will highly depends on the soil type. So each different soils type, the soil at Los Angeles, or the soil versus at San Francisco's, or like the soils that on your project site at East LA versus your project site at Long Beach. Every different site you will have different soil, and then you expect you have different like a liquid limit and plastic limit. So it's our common practice that whenever you have a new project, you will collect the soil samples, ship it to the lab, and then run those Algebraic limits, try to find the liquid limit and plastic limit for the soils you're working on site. Okay, we don't have too much time for this. So likewise, the Algebraic limit test, the details of the testing, and also the equipments wise, and all those like kind of knowledge we will talk about in 368, the Geotech Lab class. Um, but at least like my expectations for this class is for you to understand at least this figure here. You understand what is a local limit and what is a particle limit. And later on, we will also demonstrate how to use those two informations to help us for us to do the soil classifications. And the detail of the testing will be covered in 368. Pretty much like we have a week of time. We'll have like a weekly lab dedicated like the whole sections to just talk about the liquid limit tests and also the particle limit tests. And if you're interested to like to learn more details about those two tests, I highly recommend you to watch this YouTube clip. Over there, like they will walk you through using the lab equipments on about how the two tests to be done. Soil classification systems. So there's two main kinds of soil classification system. First is the USCS, which is the focus for this class. So USCS stands for Unified Soil Classification Systems. So this is very geotech based. Another soil classification system is the ASHTOS one, which is more widely used by the transportations engineers. Um, Comparing the two, the geotech one, the USCS soil classifications is more like a comprehensive, which means like there are more details instead of soil classifications. And the expectations for this class is for the students, for you guys to able to do soil classifications per USCS method. And pretty much like you can expect that like midterm exams and final exams, and you will have questions from those USCS classifications. And pretty much like from what we have learned from this lecture from the beginning, we talk about all this different type of testings, and also talk about the grain size distribution curve is get to the point that here allow us to do the USCS classifications. So the USCS the classifications is pretty much documented by ASTM D2487. So we will do the classifications according to the standard here, and pretty much like if you have questions like of course like you're welcome to come to my office hour, and if you want to have like the professionals like a reference, the STM center is also available on Canvex, and highly recommend you guys to go try to read the standard ones. You will help you to see like from the practice standards like how this being get done. Anyways, for that ASTM D2487, in order to use it, you need to know like how to use some of the key figures. So on this slide, I showed you two figures right there, which is helping us to do the classifications. First, the whole classifications setups is divided by like two categories. First is to handles the fines materials. So we talk about what is fines. So fines are the soil particles or the soils that pass through number 200, which means like those are for silt and clay. And for the USCS like classification systems, well, first of all, like these two figures are for the fines, and there's two more figures. So what I see here, actually, you have two. This is figure 3. So before it's figure 1 and figure 4, and this is figure 3. And figure 3, what I see is this: you have two parts. You have an upper part, and you have a lower part. And for those like figure 3, This is for gravels and for sand. So this figure 3 is for the coarse-grained material versus like again like the figure 1 and also the figure 4. Those are for the fine-grained material, and the difference is this one is for 50% or more passing number 200, and the other one is for more than 50% retained on number 200. So this means this is not passing. The other one is passing. And you need in order to use those like standards, or in order to be like to at the to the practice level, you need to be very precise. You need to be like very organized. And in other hands is is also need to pay attention to all the details, right? Because we talk about 50% passing and retain on the more than 50% and less than 50%, on the number two retained on number 200. But the question now is, what if you are at exactly 50% um, retained on number 200, or exactly about 50% passing of number 200? Then according to the standard, if you are right at 50%, then you should use figure 1. This means like according to the standard, you classify as a clay material or fine-grained materials if you're at exactly 50%. So those are the figures that we should use for our classifications, both for fines and also both for coarse-grained material. So the final product of these classifications, there's two parts. There's two parts. There's like what we call the group symbol. So if you use these classifications, those over here, those are the group symbols. The other fact is, in this class, we only deal with inorganic material. We don't deal with like the organic material. So this is not covered in this class. Organic materials, just is a lot more complicated. We were about like this in other classes, in more advanced classes, but this class we only focus on inorganic material. So again, soil classifications, we have two final products: the group symbols and group name. So first look at group symbols. So group symbols are those like two letters, and whenever you start with an O, those are organic material. We handle organic materials later, so the organic materials is not covered in this class. And likewise, those are all the group symbols. So it is kind of like a two letters. Most likely, most of them are two letters, of two letters over there to represent which soil groups you are at. So this is the group symbols. And if we like well, if you look at those group symbols, pretty much like you have two letters, and the first letter tells you what type of soil is. So G stands for gravel, S stands for sand. So there's more group symbols. All these are the group symbols. So also same as like a figure 1. So you have all these group symbols right there. And then after the group symbols, well, moreover, so so G is sand. Sorry, G is gravel, S is sand, and M is silt, and C is clay. So this is the first letter of the group symbols. And the second letter of the group symbol is kind of like this more elaborations or this descriptions, further descriptions of like within like a gravel, what can it be? Like within clay or silt, what can it be? Um, So that pretty much is the group symbols. And after the group symbols, we also need to handle the group names. So after this, the other part of it, all these are group names, could be long. So much more like detailed descriptions. So these are the group names. And in order to do our soil classifications, or at least the expectation for this class, is for you to able to do both group symbols and group names, starting with the information is given to you. So very likely, we'll get that for those examples. But the overview is when we give you the test results, which is uh, the Sif test, the hydrometer test, and also the Algebraic test results. You're able to, based on those test results, and then come up with the group symbols and group name per the USCS classification standard. So that's the expectations for this course, and also there's expectations for the exams. And if you take a your FE exams, they expect you to do the same thing. Same as like if you get an entry level engineering jobs, people expect you to be able to do this, able to try to understand the lab data, give you the lab data, and you're able to do your soil classifications based on the USCS. Anyways, let's walk through like this figure and how we should use those. And another trick is I group like a figure 1 and figure 4 together. Is because like actually these two figures, they kind of complement each other. So in order to do those classification systems, pretty much is you try to walk through this like a logic trees over here, or this flow chart over there, starting from the left to the right. Then you can able to finish the whole classifications, and in the midway you can get a group symbol, and at the end you can get a group name. And this figure 1 and figure 4, they kind of complement each other, because actually, like up to this part of of the classifications, this is figure 4. So figure 4 pretty much is a graphic representations of the early part of the figure 1. So if you like kind of walk through like from the left to the right, you try to figure out whether you have a liquid limit like a less than or greater than 50, and then like you look at whether your PI greater than 7, tells you whether you're above the A lines, or like be like below the U lines and stuff like that. Then pretty much is the graphical representations here. And if you look at figure 4, is the x-axis is the liquid limit, and the y-axis is the plasticity index. So we just learned this in like about 2 slides ago. The PI is equals to the liquid limit minus the particle limit. And those liquid limit and particle limits are the Algebraic test results. So they should be given to you in the homework or laboratory or exams settings. And if you're practicing, those like information is something that you will obtain from the laboratory. So pretty much like if you work for clients, then you will pay for your clients for a lab, and ship your soil samples to the lab, and those like a liquid limit and particle limit informations will come back on your desk as as a kind of like a laboratory report. But anyways, like now if according to this chart, if you know your liquid limit and plasticity index, then you should able to finish, or at least the group symbols for your fine grains material. And after you have your fine grain materials, you will further like work on this chart. So if you keep going to the right hand side, the 30% plus, the plus number pretty much is asking you whether you have uh, the soils retained on number 200. So if you have like less than 30% retained on number 200, then it belongs to this branch. If you have more than 30% retained on number 200, then you go to the lower branch. Um, and then you compare the percent sand with percent gravel, so forth and so on, and then you will at the end of the day you will get to the group name. So maybe we can get into a little bit more details on how to use those chart when we actually do some examples together. But this is the pretty much the fine grains material, the fine grains materials, and in order to to know this well, uh, pretty much the best way to learn this is by practice. Is by practice. Um, Anyways, so this graph again is um, this figure 3 is for the coarse grain material. So the way we handle sand and gravel will be a little bit different than the clay. Um, First of all, you need to determine whether you have more gravels or more sands. If you have at the beginning, if you have more than 50% retained on number 200, so within those more than 50% of materials, you compare whether you have sand more, gravel more. Then it determines whether you use the upper chart or use the lower chart. And the next thing is you look at the percent fines. So within the sand particles, or if you have a dominant a sand samples, right, you can still also have some fines on it. So if you have um, the maximum fines that you may have is 49%, right? Because if you have 51% retained on number you have 51% uh, gravel and sand and 49% silt and clay. According to ASTM standard, you still classify the overall soil samples as coarse grain material. And now you look at within the 51%, whether you have sand more or or gravel more, then you decide whether you use the upper chart or the lower chart. And within the soil samples, you look at how much a percent fines you have. In this case, you have 49% fines. Then you're qualified with greater than 12% a percent fines. Then you go to the lower part. And if you are less than 12%, then you need to have a little bit more work. You need to calculate the C sub C and C sub U, the coefficients of uniformities and coefficients of curvature. So those C sub C and C sub U, we discussed about that a couple slides before, right? So on slide number 8, we talk about the C sub U and C sub C and how to calculate them, and a little bit more explanations on slide number 9 too. So remember, those C sub C and C sub U is help us to tell whether your soil is well graded or poorly graded. So those will come back to help us to do the soil classifications. So there, you once you know whether you have sand or gravels, and then whether it's well graded, rarely graded or poorly graded, then they give you the group symbol. And you further work on the chart, this time it'll be more easy. Maybe just look at how much percent sand and percent gravel you have. Then you can get to the group name. You can get the group name. So compared with the coarse grain material, fine grain material will take a little bit more effort from the group symbol to the group name. But we can, hopefully this will make more sense to you when we try to work on examples together. Okay, those are pretty much the overview that I have for the ASTMs like a 2487, the figure 1 to figure 4. We need those figures for us to do the soil classifications. I give you some standard guidelines or some kind of procedure for you to do the whole thing. So I would say this slide number 17 is important. for this lecture, because if you want to do your soil classifications, you need to have a very clear roadmap on how to do that. And I set up this slide hopefully to help you to get there. And very important is very important. Like, this classifications at the end of the day, you know, your exams and homework, what I want to test on will be on how well you can transform those geotech informations to soil classifications. So it's clear transparency. Like in exams, it will be exactly the same thing like as what we are doing here now. Is I give you information like this, which is those like grain size distribution curve. So you have two grain size distribution curve, like two figures on the grain size distribution curve over here. So this kind of like hopefully serve as examples. So I give you 10 test results, both the grain size and also the Algebraic limit test. So you need those two set of tests in order for you to do your soil classification. So those are those test results, and there's like 10 examples here. So in this lecture, maybe we will try to finish show you like maybe 2 or 3 examples, and the rest of it I'll let you to try. And you also have the homework to practice, and also you have the textbook. If you read the textbook, they also further explain how this to be done, and also they will give you more like example problems. But anyways, the expectations is like, once I give you this uh, lab data results, you're able to to do both like group symbols and also group name according to ASTM standard. So that is the goal. And like in order to do your soil classification systems, you do your soil classifications. There's 2 main steps that I highlight. First, where importance. Once you're given like those geotech data, you need to identify these 3 numbers. What are the percent gravel? What are the percent sand? And what are the percent fines? So this also can be called percent fines. And you can tell this step, you can tell from the grain size distribution curves. For examples, let's try. Well, let's finish this first. So, percent. How can you like determine the percent gravel? It's just determined by the 100% minus percent passing, number 4. So number 4 is a sieve, right? Just like at the beginning of this lecture, when we talk about the Sieve test, we mentioned that number 4 is very important, because number 4 is the definitions of the size of the gravel. If it is like a retained on number 4, that means like it has a size of larger than 4.75 millimeters. That means those are the gravel that you have. And likewise, number 200 is also very important, because number 200 is defined by the size that of a fine grains material. So if you have the percent passing number 200, that's represent the number percent of fines. So knowing number 4 and knowing number 200 is very important. So that's why percent of gravels are those retained on number 4. So such that 100% minus percent passing number 4, that gives you the percent retained on number 4. So that is the that gives you the percent gravel. So the other one is very straightforward. Is like you want to find out the percent fines. So that will be exactly equals to the percent passing number 200. And then like percent sand will be a bit tricky, but like once you know the percent gravel and also once you know about the percent fines, percent sand will be equals to 100% minus percent gravel, and then also minus percent fines. Because whatever left over, if it is not for the stuff that is not gravel, for the stuff that is not fines, they gotta be percent sand. So first, you identify or you establish all this percentage right there. Then it helps you to move on. It helps you to move on. Okay, step number 2. Now, after you know like those percentage, the step number 2 is to find out actually which flow charts to use, because we walk through figure 1 to figure 4, but you need to identify the ones that you need for you to come up with the group symbols and also to come up with the group names. So, and you will be like a determines like by first look at how many percent passing 200 you have. If like for the case that if the percent passing number 200 is greater than 50%, then yes. If this is yes, then you know this is a fine-grained soil. Then the figure that you should use will be figure 1 and figure 4 of ASTM like a 24K7. So this is figure 1 and figure 4. So if there's like a more than or equals like a 50%, like a passing limit 200, then you go straight to this to this like a figures. For the case that if this is not more than 50% passing limit 200, then you have a coarse grain material. And within the 50%, within the percentage that are coarse grained, whether you look at like compare whether you have like a percent gravel greater than percent sand, then you use figure 3 upper. So you just classify as a gravel, then you should use like a figure 3 the upper part. But if you have the percent sand, which is greater or equals to percent gravel, so if you end up like you have 50, you have like exactly the same amount of sand equals to the gravel, then you classify as a sand according to ASTM standard. Then you will use figure 3 bottom part for you to figure out the group symbols and also the group name. So hopefully this will help you to uh, to guide you to do the whole thing. I mean, at the end of the day, to give you the group symbol and group name. And let's try a couple examples. First, let's try sample number 1. Example number 1 here. So sample number 1 means this one. So it's the blue dotted line right there. So the first step is like we need to determine. So this is example number 1. The first step, remember, the first step we do is determine the percent sand and percent gravel, and also percent fines. So percent gravel will be equals to 100% minus percent passing number 4. So which means this is the percentage retained on number 4. 100% minus percent passing means like a percent retained. So first of all, we need to identify. So when I give you the chart, I expect you to know where is number 4. So number 4 is 4.75 millimeters, and you need to know how to read the log scale, right? So this is 1, this is 2, this is 3, and this is 4, and 4.75 is here. So this is number 4. So which means this is the number 4 sieve, and I have like about 98% passing right there. So percent passing, number 4 is 98. So this is 98%. So percent gravel, we can find out this is 2%. The next, we want to find out percent sand. Percent sand is equals to percent passing number 200. And in this case, number 200 is equals to 0.0075. So this is 0.001, 2, 3, 4, 5, 6, 7. So this is 0.0075 is right here. Sorry. 0.075 millimeters is here. So this is number 200. So this is number 200 sieve, which is this data point here, which is exactly 50. So percent passing, number 200 is 50. Oh, sorry. This is not percent sand, right? This is percent fines. My bad. It's not percent sand. It's percent fines. Percent fines is like a percent passing number 200. Percent passing 200. And last is percent sand. Percent sand is equals to 100% minus percent gravel and also minus percent sand, percent fines. So which means it's 100% minus 2%, also minus 50%. So percent sand is equals to 40%. So after we determine like all those percentage, the second steps is to figure out which figures we should use. And we go back to this chart again. So do we have percent passing? So percent P means percent passing. So do we have the percent passing number 200 greater or equals to 50%? We're exactly equal to 50%. So it's yes. So which means then we should use figure 1 and figure 4 for us to finish these problems. So if we go back to figure 1 and figure 4, we also need to know the liquid limit and passing limit. And be careful, this is given as a PI, Plasticity Index. So PI is equals to the liquid limit minus the passing limit. So this problem is kind of like nice that they directly give you the plasticity index, but like very likely, the raw data you get from the lab is the liquid limit. It's not plasticity index. But anyways, this problem gives you the PI already. So we have a liquid limit like a 38 and a PI of 29. So if we go back to this chart, so now we have plastic liquid limit of 38 and 38 and 29. So if I liquid limit of 38 and also like a plasticity index of 29. So we are here. We are at this point, and this point is within the box right here. So it's a CL material. Again, we don't assume we have any organic content because organic content is out of the scope of this class. So this is a CL material. CL material. So group symbols. The group symbol is CL. Oops. Now we need to work on the group name. We need to work on the group name. So once we know this is a CL, so we go to this chart. First of all, we need to determine whether we have how much percentage retained on number 200. So we have 50%, right? Because we have 50% passing number 200, means like 50% retained on number 200, which means like we're here because we have 50%, which is greater than 30%. So we go to lower part, and then like we have percent sand more than percent gravel right here. And also we have less than 15% gravel. So that's why at the beginning you need to put down the percent gravel, percent sand, and also let's put it down. Percent gravel for example number 1 is 2%. Percent fines is 50%. So this is example number 1. This is 50%, and percent sand is 48%. Since like we have like 50% fines, which means we have this is greater than this is 50, not 5. Just make it clear. So this is 50. Whoops. So since like we have like 50% retained on number 200, so we are here. So pretty much this means like 50% passing number 200, and also we have 50% retained number 200. So this 50% is greater than 30%, so we go to the lower part, and we clearly we have like more sand and gravel, so we go here, and we have less than 15%, we go there. So the group name at the end of the day is sandy lean clay, for example number 1. Example number 1. So we are here the sandy lean clay. Group symbol is a CL. Okay, so let's try one more example. Try example number 4. Oops, let's clean this up. Let's try example number 4. Oops. Okay, on example number 4. So we are here now. We are on the yellow line. So the first step again, this is number 4, is put down the percent gravel. So percent gravel equals to the 100 minus percent minus percent passing number 4. So percent for number 4, percent passing number Sieve number 4 is about 85%. So this is equals to 100 minus 85%. So this would give me, so this is 85%, right? So give me 15% for percent gravel. Next, I look at percent fines. There will be the percent passing number 200, which is this point here. So this point is like a 45%. And then the percent sand
will be equals to 100% minus percent gravel, also minus like a percent fines. So this gives me the 40%. So for this particular samples here, number 4, we have percent gravel 15%, percent fine 45%, and percent sands to be 40%. 40%. So the next chart is to to next thing to do is like determine which figures or which like a flow chart to use. So now we ask these questions: do we have 50%, or the percent passing number 200, is that greater or equals to 50%? And the case that for us for passing number 200 now is 45%, which is less than 50%. So we are not a fine grains material. We are at the coarse grain material. So for the coarse grain material, the next questions to ask us is: do we have more gravel or more sand? In this case, we have a percent sand greater than the percent gravel. So according to STM standard, we should use the chart figure 3, the lower chart, which is here. Okay, if we use this chart, we try to walk through this. So we have percent fines, which is equals to 45% for this case. So which we have 45% is greater than 12%. So we go to this branch, the lower branch. We are there. So we have 45%. One more time, we have 45% fines, right? We have 45% fines greater than 12%. So we should go here. And the next is they ask you on the fines that you have. So we have those like 45% fines. So what the lab does is like they do the Sif Test. So they sift out the material that passing is number 200, and based on those materials, those soils particles, what they do is they perform an Algebraic limit test on those like a material, and the Algebraic limit test results to come back here. So we are sample number 4, right? We have a liquid limit of 28 and also a liquid limit of 20. So when it comes to that case, we will also use go back to this chart. So for so one more time, 28 and 20. So we have a 28 here and we have 20 right there. So we are also a CL material for the fines that we have. So using this chart now, so we are at this CL material. So the group symbol for this time now is SC. So for number 4, this is a SC material. And percent gravel is 15%. So we have 15%. So we are here. So the answer is clearly sand with gravel at the end of the day. So this is the group name. So at the end of the day, this is the answer. All right, I think we can try. You can try one last examples together. Let's do this time. Let's do examples number 7. Let's do example 7 together. So one more times, we always start with those percent sand, percent gravel, percent fines, and percent sand. So we're working on number 7. So percent gravel we have now for number 7, which is way up here, is 0%. So I skip some step over there. Well, maybe let's not skip the steps. So percent gravel is equals to 100% minus like a percent passing number 4. And percent passing number 4 here is 100%. So 100% minus 100%, we have 0%. The next is we look at percent fines. So percent fine, which is, so this is number 4 Sieve, right? We talk about there. So this is the number 4 Sieve, and this is the number 200 Sieve. So for example number 7 here, we have, for number 7, we have 8% passing number 200. So the percent fine is 8%. So because this is equals to percent passing number 200. And percent sand at the end of the day will be 100% minus percent gravel, also minus percent fines. So in our case, will be 92% to be sand. So clearly, this is a sand samples. This is a sand samples. So we figure out the percent gravel, percent fines, and percent sand. And again, like which flow charts to be used. So clearly, we only have 8% passing number 200, so it's way less than 50%. So we are here is a coarse grain material. We don't have any gravel at all, so we will use the sand flow chart, which is the figure 3 lower one. So we use this chart again. And this times, remember we have 8%. We have 8% of percent fine, so we are here. So we are here. So this require a little bit more computations work now, because this is the case that we need to find out the C sub C and C sub U. And how do we find out C sub C, C sub U? So the next thing, in order to find out the C sub C, C sub U, for us to finish the flow chart, we need to find out the D10, D30, and also the D60. Right there. So D10 for this case, remember what is D10? So D10 is the diameter at 10% passing. So 10% passing means like if we go to the 10% on the y-axis and we go back to the curve, whenever we hit the curve, so this is our D10. So D10 is about, for this case, is about 0.075, no, 85. So if you read the log scale, right? So this is 0.08, and here is 0.09, and we are between them. So D10 is 0.085 millimeters. And likewise, we need to find out D30. And D30 is the one that we go to 30% passing. And we go to this chart. So this is about 0.018. So this is log scale. And then we also need to do the D60. Oops. We go to this curve. Then we go down again. So D60 will be about, so this is 0.1, 0.2, 0.3, 0.4, 0.5, about 0.59. So D60 is about 0.59 millimeters, right? 0.1, 0.2, 0.3, 0.4, 0.5, 0.59. So after you determine those D10, D30, and D60, then we can calculate the C sub C and C sub U. So C sub U is equals to D60 divided by D10. So which is equals to 0.59 divided by 0.085 millimeter this times. So if we do our math, 0.59 divided by 0.085, we get 6.94. Likewise, we also need to find out the the C sub C, which is D30 squared divided by D10 times D60. So which is 0.018 squared. D10 is 0.085 and then times 0.59. So if we do our math here, we get 0.646. Let me double check one more time. Yes, we get 0.646. So we get these two numbers now. We go back to what we have learned previously. So one more time, C sub C is 0.694, and C sub C is 0.646. Okay. Remember, like we learned about how to determine this is well graded or poorly graded. So if we go back to this chart here now, so in order to be well graded, it is you need to fulfill these conditions. And in order to be poorly graded, you need to fulfill these conditions. And now we have, for these examples, we have C sub C equals to 6.94, and our C sub C is equals to 0.646. So C sub C is greater than 6, yes. But now our the C sub U is greater than 6. So this is C sub U, my bad. So this is C sub U is greater than 6. So you fulfill the first conditions. But the C sub C is not between 1 and 3. So this is not a well-graded material because you need to fulfill both of them. So this is a poorly graded material because you fulfill the case that C sub C is less than 1. So whatever three scenario for the poorly graded, you fulfill one of them, then you belongs to the family of poorly graded. So and if you walk through this chart, you will have the same thing too, because we are at a fine contents 8% for example number 7, which is here, and our C sub one more time. Our C sub C is 6.94. Sorry, C sub U is 6.94, and C sub C is 0.646. We just calculate them based on the D10, D30, and D60. And we are at the case that we are here because everything is all, right? We fulfill the C sub C that is less than 1. So we fulfill the scenario. In order to be well graded, you need to have an AND conditions, but we are not there. So we don't fulfill this AND conditions. So that's why we go to the lower part. Okay, the next solving this chart, going with this flow diagrams, now we need to look at the finds, what kind of finds we have. So whenever they look for the finds, then you need to go back to figure 4. But anyways, for samples number 7, so we keep solving for sample number 7. We have the finds. This case, the local limit is dash, and then the positive limit index is dash, which means like they test on the percent fines, but it turns out it's not sticky at all. There's no cohesions. So both the liquid limit, so this means both the positive index, the liquid limit and positive limit, both is equal to 0. So the plasticity index is also equal to 0. So in that case, you are here, 0, 0. You are at the box of ml. So 0, 0 means ml material. So if we go back to this chart, we are at the ml material. So we keep working on the full chart. So now we are at the SPSM. So the family that we have, the group symbols that we have is SPSM. And do we have less than 50, how much percent gravel? We have 0% gravel for this example. So we have less than 15% gravel. So at the end of the day, our group name is poorly graded sand with silt. Sand with silt. So that's our final answer. So you can imagine that, like, when you're working on sand samples, you may take a little bit more computations because you need to find out the C sub C and C sub U. So I have solved for like 3 examples problems here, and highly recommend you practice all of them. And I uploaded the solutions for this slide on Canvax, so you can check your answers too. And exams, will be the same thing. I give you like a green side distribution curve, and then like ask you, and also Algebraic limit test, and ask you to come up with the group symbol and also group name. But the expectation is the exam is you need to do it like efficiently. It's not something like during exams you have another extra 30 minutes to over there to solve for one problem. Pretty much I expect you like with like less than 15 to max 15 minutes, less than 10 minutes, maybe maximum 15 minutes. You can come up with the group symbols and also group name. So with this, I conclude lecture number 2. Highly recommend you to practice with any chance you can. And those homework problems you need to work on too. But if you have any questions, please come to my office hour or shoot me an email. Thank you so much. Bye bye.